Hello everyone, welcome back to our channel Cognitives, and this is your mentor Rahul Ghosh. In this interesting episode, we are going to dive deep into the mystery of lateral inversion. Let's begin the learning.
Look into a mirror. What do you see? You see yourself, of course. But have you ever noticed something peculiar about your reflection? Take a closer look. You see yourself, of course. But something is a little off. Your reflection seems familiar, yet there's an oddity that you can't quite put your finger on. But something is a little off. Your left side appears to be your right, and vice versa. This isn't just a trick of the eye, it's a fundamental property of how mirrors work. Your left side appears to be your right, and vice versa. This curious phenomenon is called lateral inversion. It's a fascinating concept that has intrigued scientists and lay people alike for centuries. This curious phenomenon is called lateral inversion. Lateral inversion is the flipping of an image along a vertical axis. Imagine a line running from your head to your toes, dividing your body in half. Lateral inversion is the flipping of an image along a vertical axis. This means that the left and right sides of your reflection are swapped. Imagine a line running from your head to your toes, dividing your body in half. This line acts like the mirror's axis. Off the mirror, it creates an image where the left and right sides are swapped. This line acts like the mirror's axis. When light reflects off the mirror, it creates an image where the left and right sides are swapped. This flipping doesn't happen along the up-down direction, so you don't appear upside down. This flipping doesn't happen along the up-down direction, so you don't appear upside down. This is because mirrors reflect light in a way that preserves the vertical orientation of objects. This flipping doesn't happen along the up-down direction, so you don't appear upside down. Lateral inversion is a fundamental property of how mirrors reflect light. It's something we encounter every day, often without even realizing it. Lateral inversion is a fundamental property of how mirrors reflect light. It's something we encounter every day, often without even realizing it. Think about the last time you looked in a mirror. Did you notice how your reflection was laterally inverted? It's something we encounter every day, often without even realizing it. It might seem simple, but lateral inversion has fascinating implications for how we perceive the world around us. From everyday objects to sophisticated scientific instruments, understanding lateral inversion is key to understanding how we see and interact with our reflections. It might seem simple, but lateral inversion has fascinating implications for how we perceive the world around us. For instance, when you look at text in a mirror, it appears reversed. This is why ambulance vehicles have the word ambulance written in reverse on the front, so that drivers can read it correctly in their rearview mirrors. From everyday objects to sophisticated scientific instruments, understanding lateral inversion is key to understanding how we see and interact with our reflections. Mirrors are used in a variety of scientific instruments such as telescopes and microscopes, where precise reflection and inversion of images are crucial. By understanding lateral inversion, we can better appreciate the role mirrors play in both our daily lives and in scientific exploration. Lateral inversion isn't just a scientific curiosity, it's something we experience constantly. It's a phenomenon that subtly influences our daily lives in ways we might not even realize. From the moment we wake up and look into the bathroom mirror, to the time we check our appearance in a shop window, lateral inversion is at play. This fascinating optical effect is not just limited to mirrors, it extends to various reflective surfaces we encounter throughout the day. Take a look at the text on an ambulance or a fire truck. Have you ever noticed that the word ambulance is written in reverse on the front of the vehicle? This is done intentionally. When drivers see the reflection of the ambulance in their rearview mirrors, the reverse text appears correctly oriented, allowing them to quickly read the word and respond appropriately. This simple yet effective use of lateral inversion can save precious seconds in emergency situations, potentially making the difference between life and death. It's written in reverse. Why? So that when drivers see the reflection in their rearview mirror, the words appear correctly flipped and are easily readable. This clever design ensures that the message is conveyed instantly, without any confusion. Imagine the chaos if the text were not reversed. Drivers would struggle to decipher the message, leading to delays and potentially dangerous situations on the road. Another relatable example is the humble clock. Clocks are everywhere, from our homes to public spaces, and they too demonstrate the principles of lateral inversion. When you look at a clock's reflection in a mirror, the numbers appear reversed. This can be quite disorienting at first glance, but it serves as a perfect illustration of how lateral inversion works. Look at a clock's reflection in the mirror. The numbers appear reversed. This reversal can make it challenging to tell the time if you're not accustomed to interpreting mirrored images. However, it also provides a unique perspective on how our brains process visual information. By understanding lateral inversion, we can better appreciate the complexities of our visual perception. The hour hand that points to the 3 on the actual clock seems to point to the 9 in the reflection. This switch in positions is a direct result of lateral inversion, and it highlights how our perception of direction and orientation can be altered by reflective surfaces. It's a small but fascinating detail that underscores the importance of understanding optical phenomena in our everyday lives. This reversal highlights how lateral inversion affects our perception of direction and orientation. It can be particularly noticeable in situations where precise visual information is crucial, such as driving or reading signs. By being aware of lateral inversion, we can better navigate our environment and make more informed decisions based on the visual cues we receive. Even something as simple as waving your left hand in the mirror demonstrates lateral inversion. When you wave your left hand, your reflection appears to wave its right hand. This simple action is a clear and immediate example of how lateral inversion works. It's a fun and interactive way to observe the effects of this optical phenomenon in real time. Your reflection appears to raise its right hand. This mirrored movement can be amusing and sometimes even confusing, especially for young children who are just beginning to understand the concept of reflections. It's a playful reminder of how our visual world is shaped by the principles of optics. A plane mirror, the flat, everyday mirror we use, is the master of lateral inversion. This phenomenon is something we encounter daily, yet it often leaves us puzzled. When we look into a mirror, we see ourselves, but something seems off. Our left and right sides appear to be swapped. This is what we call lateral inversion, and it's a fascinating optical illusion that has intrigued scientists and laypeople alike for centuries. But how does it pull off this visual trickery? To understand this, we need to delve into the science of light and reflection. Mirrors have been used since ancient times, not just for personal grooming but also for scientific experiments and artistic endeavors. The way a mirror manipulates light is both simple and complex, rooted in fundamental principles of physics. The answer lies in how light interacts with the mirror's surface. When light rays hit a mirror, they don't just stop or pass through, they bounce back. This bouncing back of light is what we call reflection. The surface of a mirror is smooth and polished, allowing it to reflect light in a very predictable manner. This predictability is key to understanding how mirrors create images. When light from an object, like your smiling face, hits the mirror, it doesn't pass through it. Instead, it reflects off the surface. This reflection is governed by the laws of physics, specifically the law of reflection. This law states that the angle at which the light hits the mirror, known as the angle of incidence, is equal to the angle at which it bounces off, known as the angle of reflection. Instead, it bounces off the smooth surface. This bouncing or reflection follows a specific law. The angle of incidence, the angle at which light hits the mirror, equals the angle of reflection, the angle at which light bounces off. This principle is what allows mirrors to create clear and accurate reflections. It's also why mirrors are used in a variety of optical devices, from telescopes to cameras. This bouncing or reflection follows a specific law, the angle of incidence. The angle at which light hits the mirror equals the angle of reflection, the angle at which light bounces off. This principle is fundamental to the way mirrors work. It ensures that the light rays reflecting off the mirror create a coherent image that we can recognize. Without this law, mirrors would not be able to produce the clear reflections we rely on. Imagine lines extending from each point of your body to the mirror and then bouncing back to your eyes. These lines represent the paths that light rays take as they travel from your body to the mirror and back to your eyes. Because of the law of reflection, these lines create an image behind the mirror that is the same distance from the mirror as you are. This is why your reflection appears to be the same size as you, but flipped. Because of the law of reflection, these lines create an image behind the mirror that is the same distance from the mirror as you are. This image is a virtual image, meaning it cannot be projected onto a screen. It exists only in the perception of the observer. The virtual image appears to be behind the mirror, but in reality, it is a construct of the light rays reflecting off the mirror's surface. However, due to the way these lines intersect, the left and right sides of this image are flipped. This flipping is what we perceive as lateral inversion. It's a direct result of the way light rays reflect off the mirror and enter our eyes. Our brain interprets these light rays and constructs the image we see. The left-right inversion is a fascinating quirk of this process, one that has puzzled and intrigued people for centuries. What we perceive as lateral inversion is simply our brain interpreting this flipped image. Our brain is incredibly adept at making sense of the world around us, but sometimes it can be tricked by optical illusions like this. Understanding the science behind lateral inversion not only gives us insight into how mirrors work, but also into how our brain processes visual information. It's a reminder of the complex and fascinating nature of both physics and human perception. Periscopes, those ingenious devices used in submarines and trenches, rely on mirrors to bend light and allow us to see around corners. But they also provide a fascinating example of how lateral inversion can be manipulated. A basic periscope consists of two plane mirrors placed parallel to each other and angled at 45 degrees. Light enters the top mirror and is reflected downward to the bottom mirror. The bottom mirror then reflects the light horizontally to the viewer's eye. Now you might think that with two reflections, the image in a periscope would be flipped twice, canceling out the lateral inversion. However, the geometry of the mirrors ensures that while the image is flipped vertically or upside down, it remains laterally inverted. The final image we see through a periscope is both upside down and laterally inverted.
That's all folks. So आज के सेशन में बस इतना ही. Hopefully this session was useful and interesting for you. So thanks a lot for watching and do stay connected with Cognitives for getting update on the next module. See you guys.